Okay, let's dive right into this explainer by completely tossing out the idea that you have to rote memorize some massive, intimidating chart of numbers. Seriously, if you've ever felt totally overwhelmed by all the fractions and square roots popping up in trigonometry, I've got a massive secret for you. We don't need a photographic memory to master this. The unit circle is actually this incredibly elegant cheat sheet, and it's built entirely on basic repeating patterns. And I promise you, once you see the pattern, you literally won't be able to unsee it.
We're going to start with the absolute simplest building blocks and work our way up. Here's our roadmap. First, we'll meet the unit circle. Then, uncover the secret triangle connection. Link that to sine and cosine, reveal quadrant patterns, and finally, solve problems with the circle.
Section 1. Meet the unit circle. So the absolute most crucial thing to grasp right off the bat is that this isn't just some random circle, it's perfectly placed. Its center sits dead on the origin of an xy coordinate plane, 0, 0. And the distance from that center to the outer edge, the radius, is exactly 1. Always 1. That 1 is literally where the unit in unit circle comes from. And as we'll see, it's the magic number that makes this entire system work so flawlessly.
And this right here brilliantly illustrates why mathematicians are so obsessed with the unit circle. Just think about the standard, clunky equation for a circle, where you have a and b messing up the center and r for the radius. By dropping our center perfectly at 0 and forcing that radius to be exactly 1, all those extra annoying variables just vanish. That complicated equation transforms into the beautifully simple x squared plus y squared equals 1. This tiny little equation, it's the engine driving our entire cheat sheet.
Section 2. The secret triangle connection.
Now imagine dropping a right triangle right inside our circle. Pin the tip of the triangle at the center origin and stretch its longest side, the hypotenuse, out until it touches the circle's edge. Well, because the radius is 1, our hypotenuse is exactly 1. By slotting in special right triangles, specifically your classic 30-60-90 and 45-45-90 triangles, we map out the absolute most vital x and y coordinate links for the first quarter of the circle. Take a 30-degree angle. Its width, or x-coordinate, is the square root of 3 over 2, and its height, the y-coordinate, is exactly 1/2. Go to 45 degrees, and both the width and height perfectly match at the square root of 2 over 2. Bump it up to 60 degrees, and they just flip. The width becomes 1/2, and the height becomes the square root of 3 over 2.
Section 3. Connecting sine and cosine. Remember SOHCAHTOA from geometry class? Well, if we follow that exact logic step by step for the cosine ratio, which is the adjacent side divided by the hypotenuse, we stumble onto something amazing. Our adjacent side is just the horizontal x-coordinate, and the hypotenuse, we just established that's the circle's radius, which is 1. So dividing that adjacent side x by the hypotenuse 1 proves that the x-coordinate is exactly the cosine of the angle. Yep, it's really that simple. X just equals cosine.
Following that exact same chain of logic, sine is the opposite side over the hypotenuse. Our opposite side is the vertical height, the y-coordinate. And y divided by 1 is, well, it's just y, which means y perfectly equals the sine of the angle. The huge takeaway here is that you aren't memorizing random plot points on a graph. You are literally just looking at the cosine and sine values sitting right there in front of you. Every single xy coordinate on this circle is just a secret code for cosine sine.
Section 4. Quadrants and easy patterns.
Okay, before we venture out into the rest of the circle, I have to show you this. Look at how beautifully the first quadrant builds. There is literally a hidden counting pattern. Look at the y-coordinates, the heights, climbing from 0 degrees up to 90 degrees. They just count up from 0 to 4. It goes the square root of 0 over 2, the square root of 1 over 2, the square root of 2 over 2, root 3 over 2, and the square root of 4 over 2. And since the square root of 4 is 2, and 2 divided by 2 is 1, boom, it perfectly lands on a height of 1. It's just counting 0, 1, 2, 3, 4, all under a square root, all divided by 2. And the x-coordinates? They do the exact same thing, just running backwards from 4 down to 0.
So, what about the rest of the circle? Well, because the other 3 quadrants are just mirrored reflections of the first one, the numbers themselves are completely identical. The only thing that actually changes is whether those numbers are positive or negative. And to figure that out, we only need this incredibly handy acronym from the source material. All students take calculus. Starting in the top right and moving counterclockwise, A stands for all positive. S in the top left means only sine is positive. T in the bottom left means tangent is positive, and C in the bottom right means only cosine is positive. That's it. All students take calculus. Now, what if you get thrown a curveball?
What if you encounter some massive angle like 450 degrees, or even a negative one like negative 270 degrees? Don't panic, just remember they are coterminal angles. Think of them like runners doing laps around a circular track. No matter how many times they run around, they land on the exact same physical spot on the unit circle, meaning their trig expressions are perfectly equivalent. 450 degrees is really just a full 360-degree lap plus an extra 90, so it stops at the exact same spot as a standard 90-degree angle.
Section 5. Solving with the circle. All right, let's actually test out this tool we just uncovered with a practical example. Does the coordinate point 1/4 actually sit right on the boundary of our unit circle?
To figure this out, we just go right back to that beautiful, simple formula from the beginning, x squared plus y squared equals 1. By plugging the x and y values of 1/4 into our formula, we get 1/16 plus 1/16. Add those together, you get 2/16, which easily simplifies down to 1/8. And, well, we can definitively prove that 1/8 does not equal 1. Because it doesn't equal exactly 1, that point completely misses our circle's edge. It's hovering somewhere inside it, but it's not on the circle.
Let's step it up and try finding a specific trigonometric value. How would we evaluate the cosine of 135 degrees and do it without reaching for a calculator?
Okay, first, we pinpoint where 135 degrees is. It sits in the second quadrant, top left. And look at that, it exactly mirrors the 45-degree angle from our first quadrant. Our cheat sheet already tells us the 45-degree coordinates are √2/2 for both the x and the y. But remember our acronym, all students take calculus? In the second quadrant, the students' quadrant, only sine is positive. Everything else has to be negative. So, using our mirror logic and knowing that cosine is always the x value, we can instantly decode that our answer must be negative. Therefore, the cosine of 135 degrees is negative square root of 2/2. Simple as that.
Let's do one final, slightly tricky example involving tangent. What is the tangent of 270 degrees? This one sits right at the very, very bottom of the circle, straight down on the y-axis. Down at 270 degrees, our exact coordinate point is 0, -1. The x is 0, the y is -1. Now remember the rule for tangent? Tangent is sine divided by cosine, which means it's the y-coordinate divided by the x-coordinate. So we end up trying to divide -1 by 0. And as we all know, dividing by 0 in math pretty much breaks the universe. It gives us a mathematically undefined result. So the tangent of 270 degrees is, quite simply, undefined.
So, as we wrap up this explainer, I really want you to remember this empowering thought drawn straight from our sources. If we know the first quadrant and those simple counting patterns, we literally know the whole thing. You don't need a photographic memory to conquer trigonometry, you just need to understand the underlying pattern. And it honestly makes you wonder, if something as notoriously complex as the unit circle turns out to be just a simple counting pattern hiding in plain sight, what other hidden patterns in math, or even in the world around us, are just waiting for you to decode them?